Okay, we're going to start our waves unit. And to start off, we're just going to give a definition. A wave is a transfer of energy by vibration of a medium. A medium is just the material that the wave travels through. So for example, a water wave, the medium is water. For a guitar string, it's the string itself. For a sound wave, the medium is air. Now, there's two types of waves that we need to talk about and know the definition for. One is a transverse wave. And the definition of that is the medium vibrates perpendicular to the energy. I'm going to use a fancy word, propagation. And that just means that the way the energy is being transferred, or the direction the energy is moving. And they're going to look like what we think of when we think of waves, something like this. Okay? If I look at just one particle on the medium, that particle is going to vibrate up and down as the energy moves to the right in this example. And that particle itself is not going to be transferred. It's not going to move to the right. It's not going to go from one place to the other. It's just going to vibrate up and down until the energy has all gone through, and then it's going to come back to its equilibrium position. Examples of these are water waves. If you go to the beach, you see waves that look like this, light, and so on. There's many. Okay, most things we think of as waves are going to be transverse waves. Now, I'm going to show you a diagram of a transverse wave, and then of the next time, which is a longitudinal wave. Longitudinal waves are a little bit hard to draw, so I want you to see what they're going to look like. So for my transverse wave, when I start this out, there's going to be energy coming from the left and moving to the right. And if you just look at the lighter colored particle in here, you're going to see that it just goes up and down as the energy goes through. So I hit start, and the particles are moving up and down. The particles themselves aren't moving to the right, they're just vibrating up and down. Now, for a longitudinal wave, they're going to vibrate parallel. Instead of vibrating perpendicular, they're going to vibrate parallel. And so if you just look at that lighter colored particle in there, it is going to vibrate back and forth as the energy goes. So if I hit start, there they're going through, okay? And if I stop it for a moment, you're going to see that there are places where the particles are denser, more closely packed together, and places where they're more spread out. And then as I start it again, okay, you can see them moving back and forth. The particles themselves aren't being transferred to the right, they're just wiggling, vibrating back and forth. So back to our notes. I'm going to try to draw that. Okay, so we are going to start out by drawing our little particles. And let's say right here, as they've been vibrating back and forth, at this moment they're kind of spread out. Then they get squished together here, and then more spread out over here, and then squished together over here, and so on. Okay, these guys are vibrating back and forth this way, which is parallel to the direction the energy is moving. So we want to say for the definition for these that the medium vibrates parallel to the energy propagation. for our longitudinal waves. And our example for this, if you took a slinky and pulled it back and let go of it, it would do that. But the one that's important is sound. Sound waves are the air molecules vibrating back and forth parallel to the direction that the sound energy is being transmitted. Now, wave properties, things that we are going to measure on the wave. First thing is a cycle, and this is one repetition, okay, until the wave repeats itself. So if I label this top point, point A, I'm going to give you a definition here. We call the high points on the waves crests, and then over here is B. All right, that's going to be one cycle because I've come back to the same spot. So we'll label that from A to B is one cycle. If I start down here at the bottom, maybe label that one C. The points on the bottom we call troughs. When I get to the next trough, label it D, that also is a cycle. So C to D. I'm going to label some points on here. If I call this E, F, and G, E to F is not a cycle because it's not repeating. It's back at the same height, but it's not going in the same direction. So I have to go all the way to G to get to one cycle. So C to D is one cycle, and E to G is going to be one cycle. Wavelength is the distance for one cycle. Okay, you can measure crest to crest, that distance, or if I measure this distance from here, basically what you would think of as 360 degrees for a sine wave, that could also be one wavelength. Now, our letter for wavelength is going to be the Greek letter lambda, looks like this, okay? And so if I measure this distance, that is one wavelength. Okay, so for our example up above, I'm going to label another point. Let's call this, let's see, we got up to G, we'll call this H. I have a distance from A to H. From A to H is 3 cycles. Because if I start at A to B is one cycle, B to the next crest is a second cycle, and then from there to H is a third cycle. So I have 3 cycles, and I know that's 6 meters. I could even label my wavelength would be like from crest to crest, so that distance there would be the wavelength. Well, if this whole thing is 6 meters and there's 3 cycles in there, each cycle has to be 2 meters. So the wavelength is going to be 2 meters for that example. Our frequency is how fast, how frequently the wave repeats. Okay, it is the number of cycles per second, sometimes you see it that way, or the number of waves per second. And the letter for it is going to be F for frequency. So for the example up above, again, from A to H is 3 cycles, and that took 5 seconds. So let's make that. So from A to H was 3 cycles in 5 seconds. So my frequency is going to be 3 cycles per 5 seconds, which is 0.6 cycles per second. Now, a cycle per second, an abbreviation for that is hertz, so I might rate it as 0.6 hertz for the frequency. Top of the next page, we're going to define period. The period is the time for one cycle. So we might say that it is seconds per cycle. The letter for it is capital T. Now, seconds per cycle, you notice frequency was cycles per second. This is seconds per cycle, so they're inverses. So the period is 1 over the frequency. So the bigger the frequency, the faster it's repeating itself, the shorter the period is going to be, and vice versa. They're inverses. So for our particular example, we had a frequency of 0.6, so our period is going to be the reciprocal of that, 1 over 0.6, and that's going to give us 1.66 repeating seconds per cycle for our period. The amplitude is the maximum displacement from equilibrium okay? It's almost always going to look like height for these. And if I go back to our example on the other page, we can see that the total height for this wave from the bottom to the top was 3 meters. But that's not the definition for amplitude. The amplitude is distance from equilibrium, so it's going to be half of that 3 meters, or 1.5. So we'll write that down on the next page. We are going to get that the amplitude in this case is 1.5 meters. To find the velocity or speed of a wave, velocity, now let's think about this. Velocity is distance divided by time. Now the distance for one cycle is the wavelength. The time for one cycle is the period. So when I calculate the velocity for this one, our wavelength was 2 meters. We have that on the previous page. And our period was 1.66 repeating seconds. And oh look, I have meters per second. That's going to be a velocity. And we're going to end up with a value of 1.2 meters per second. Now that's not usually how you calculate it. I just wanted you to see how if we do wavelength divided by period, that's distance over time, gives me meters per second. The equation we're really going to use almost always, and this is like the F equals ma for waves, velocity is wavelength times frequency. If we do the same example, our wavelength was 2 meters, and our frequency was 0.6 hertz, and that would also give us the value of 1.2 meters per second. So when you think velocity, I really want you to think this v equals lambda f. I can use wavelength divided by period, but usually they're going to give you frequency and not period.